Alright, ladies and gentlemen, well, I found out through trying to change quality levels of video capture it didn't work. So I apologize for the quality. I'll get better at it as time goes by. We're going to be on chapter 5 now, part 1 of 2. I'm going to do the same thing, go through each slide. So get your slides out for chapter 5 and let's move on. We're going to talk about the hydrologic cycle now. In slide 2, I guess we have all seen Kevin Costner's movie called Water World. Well, Earth has been called Water Planet many times, as not necessarily 3/4 of the Earth's surface, but 70.8% of the Earth's surface is covered by water. So it's a very appropriate term to call this the Water Planet. It's unique in that it can simultaneously exist regarding water. It can exist in all 3 states of matter on this planet. This is the only planet we know that water can exist in one location, in solid ice, liquid water, and water vapor. And at the same temperature and shift between states easily. At 32 degrees we have ice, water, and water vapor. The hydrologic cycle refers to the cycle of water through the earth and the atmosphere. So if we move on to slide 3, that is a great picture to show you the entire hydrologic cycle. Now, how long does it take? There have been debates on how long a water molecule, goes from the ocean up to the clouds, condenses, falls, precipitation, travels through the surface back to the ocean. There are different explanations. 100 million years I've read. Others have dictated the hydrologic cycle in other ways, but what you have is evaporation from the ocean, condensation in cloud formation, precipitation as a result. Can have some horizontal movement before precipitation occurs, and then it lands on the mountains, for example. Can land anywhere, but mountains in this picture. And then it transports particles, material, as it travels through soil, downhill, if you will, back to the lowest point on the earth that it can get, and that is the ocean, typically. Next slide is regarding that water vapor and the liquid water. We have evaporation and condensation. We don't call it rain, we call it condensation. So condensation is just prior to precipitation. We call it molecules that escape the overlying volume of water, called evaporation. It takes energy to do this, and it's amazing how that it takes the sun provides just the right amount of energy to break apart those water molecules, just the right amount of water molecules off the ocean, in order to maintain an energy balance throughout the earth. Water vapor increases in air as surface water evaporates. So we lose it in the ocean, we gain it in the atmosphere. The molecules, they randomly collide with water surface, and they bond with adjacent water molecules, and this is what we call condensation. There is an equilibrium between evaporation and condensation, and when they both are relatively equal to each other, we call that saturation. Upon saturation, condensation begins, and water returns to the surface in the form of precipitation. The air atmosphere doesn't hold water vapor. Okay, water vapor exists in as a gas, and just like any other atmospheric gas, oxygen, nitrogen, it can go away tomorrow. It's not there all the time. It's called a variable gas as a result. So evaporation and condensation occurs, and it is in equilibrium throughout the earth. So just a very small portion of the ocean evaporates. but at first there's no water vapor in the air. Then over time, evaporation occurs in a flat water surface, and evaporation occurs at a certain rate. The evaporation rate is equal to the condensation rate. So eventually the evaporation rate, when the evaporation rate equals the condensation rate, we have saturation. Alright. Slide 6. Sublimation is the time when solid water, ice, changes into water vapor without going through the state of liquid. Okay. Also, water vapor can change directly into ice or even snow, which are both solids, which is the opposite. They call that deposition. Alright. Now, next slide is we have indices of water vapor content. So, one index that we use is humidity, which we're all familiar with in San Antonio, Houston. If you've ever been on the coast, in other areas of the world where humidity is very high, you can think of them. And you can also think of the opposite, where humidity is very low. You've been to those places as well. So humidity is the amount of water vapor in the air. It's expressed through a few ways. It has advantages and disadvantages depending upon the use, but it refers to water vapor. It's not a solid, it's not a liquid state of water, it's not ice, it's not snow, it's not rain. It's water vapor, the gas. The next slide is vapor pressure is another index for water vapor content. Vapor pressure, amount of pressure exerted in the atmosphere by the water vapor. Okay, it's the amount of pressure exerted. It's dependent upon both density and temperature of the water vapor. Next slide is vapor pressure has a saturation. When the evaporation and condensation, the rates equal each other, we have saturation vapor pressure. That's when the atmosphere is saturated, and that movement of water vapor molecules exerts vapor pressure on the surface of the earth. Okay, you don't feel it, but when the humidity is very high, you can almost feel it. It's uncomfortable. Next slide, 10. Saturation vapor pressure is temperature dependent. Lower temperatures, saturation vapor pressure increases. It increases, alright? But it increases slowly. It increases rapidly at higher temperatures. That's all about energy transforming to kinetic energy. It's not a linear increase. See how we're doing on time. We'll go one or two more slides and take a break. Okay, so there's a nonlinear increase in saturation vapor pressure with increase in temperature. Absolute temperature. Absolute humidity. So we have water vapor content in the atmosphere called humidity. But there's absolute humidity, which is the density of the water vapor expressed as a number of grams per cubic meter of air. Mass per volume. Number of grams of water vapor per cubic meter. The absolute humidity value changes as air volume expands and contracts because of the volume. If it expands, then the absolute humidity goes down. If it contracts, the absolute humidity goes up. Alright. Specific humidity, and we'll take a break right here after this. Specific humidity represents a given mass of water vapor in a given mass of air. Water vapor in the mass of air. Mass to mass. Specific, meaning it's unitless. That's what specific means. So specific humidity does not change as air expands. So it's the mass of water vapor per mass of air. Okay. In other words, we can talk about that later, but and I can give you some homework assignments to in class. We might have a pop quiz to go over the numbers. But saturation specific humidity is the specific humidity of the temperature when it is saturated. Specific humidity is a given mass of water per a given mass of air. Saturation specific humidity is the specific humidity of the atmosphere when it is saturated. Okay, I know it's probably not clear right now, so let's take a break and capture your thoughts, and we'll pick up on part 2 of 2. This is still going to be part 1, but let's take a short break.